Hello, this is Dead Hamster. Today I'm going to give an update as to what's been going on recently with the build of OverKart 64. I've been showcasing Peach's Castle custom course recently as well as a sort of placeholder, but unfortunately I haven't had much updates as to what's actually going on with OverKart 64 itself, the program that is used to create custom courses. With this newest build, a lot of things have come up during its production, and every time I kind of get a little bit closer towards finishing it, we come up with maybe a new concept or a new idea. Hot swapping was a very big one, and right now the build of OverKart completely supports it. Hot swapping is completely implemented. Everything should be working to the point where we can store 64 custom courses on top of the 16 stock ones, and that is an arbitrary limitation. Theoretically, we can store unlimited custom courses. 64 is just a rather iconic number. However, when attempting to build Peach's Castle and get it to load in the game, I have been unable to, and I've probably recorded roughly 3 hours worth of footage of me debugging and looking through different theories as to what was wrong. I did figure out quite a few things that were perhaps done a little funny or a little wrong, but they wouldn't be why the course wasn't loading, and I couldn't really figure out what was going on. When looking into the RAM, I noticed that data was just getting absolutely clobbered, and it started to offset 237948 hexadecimal. Couldn't really figure out what this was. Looked at other courses, and there was nothing specifically at that offset. So I compared the RAM dumps of my custom course having crashed, a regular course loading in full, and the RAM right before a course was to be loaded. And by comparing those and looking at the data and seeing what the data was that was there in each of the three, I was able to determine that the game was unpacking the compressed segments. After it uncompressed them, it was writing them into this section of RAM. And it wrote them in reverse order so that they would end at 1DF00. I'm probably messing that up. I have it written down somewhere here on notations, but I don't know. Yeah, unfortunately, I do not know offhand what that offset is, but I do have it recorded somewhere. It's rather irrelevant at the moment. The point is that it unpacks data ending at that offset and then works backwards. First unpacks segment 7, and then segment 4, and finally segment 5. And segment 5 is texture data. It's just raw texture data. The way that it's assembled is actually by parsing through segment 9, we read the texture list that's stored in segment 9, and that contains offsets to individual textures, and those are all individually compressed with MIO0 compression. I use Daniel McCarthy's PEEPS compression, which is an open source C# library for handling MIO0 compressing and decompressing. It has worked fine for the segment data, but when Mario Kart decompresses my segment 5 data, it processes the first few textures fine, but when it gets to the 6th or 7th texture, that's when it completely crashes, and it seems that it's writing a byte out of order, and then a butterfly effect takes hold, and everything else is just completely clobbered from there. And what I think is happening is that some parameter is out of check with how the PEEPS compression is dealing with the MIO0 compared to how Mario Kart 64 is dealing with it. And whereas in the segment data, it normally wouldn't matter, but for bitmap data, there's just so many pixels and so much data that's repeating. Eventually, it just kind of catches a snag where this is expecting A and this is expecting B, and the two just aren't working together. The way the MIO0 compression works is that it will say, write this much data from uncompressed section, write this much data from the point that you've already written up into the section here. and then so you write that data, and that's how it compresses itself, because you're rewriting data that already exists in the file. In some cases, you may be at offset 15, and it says rewrite data from 10 to 25. And you're like, well, I'm at 15, 20, 25, 17, these don't exist. But they will by the time you get there. Now you start at 15, you write 10, 11, 12, and now you're at 18. And as you move forward, you write the data that you had just written. So it sort of chases its own tail, is the term that a lot of people use. Again, these kind of intricacies to the compression algorithm definitely could be a reason why there's that discrepancy. If you think about zip compression, which is very similar, LZ77 is the basis for all of this, so to speak. You zip up a file with WinRAR compared to Windows compared to 7-zip, and they're all going to be three drastically different files with different file sizes and different structures to how the bytes were written out. And in this case, I just don't think Mario Kart 64 is flexible enough to deal with the compression of the textures that we're getting from the Mr. Peeps compression from Daniel McCarthy. Fortunately, I think I may have a workaround. It again comes from Micro 500. When he designed his courses for Micro Mountain, he did not compress anything. In fact, his MIO0 compressed files are larger than their source inputs. And we're going to go ahead and take a look right now as to why that is, how it was accomplished, and why I think it's going to benefit me and OverKart in getting this to work. To preface, there are 4 libraries that I found that deal with MIO0 compression. Daniel McCarthy's Peeps compression is the only one in C#. OverKart 64 is a C# program. I do not think that I'm smarter than he is. I think that he's much more capable at writing a decompression and compression algorithm than I am, and I don't think that I would be able to improve upon his work. And the only other alternative to this cheat that I can think of is that Mario Kart 64 actually has its own compression algorithm written into the game code, which most video games do not. Most games will have the decompression written in because they need to read the data that's already been written to the file. But for the most part, the compression tools themselves are going to be in the developer tools that are used to create the content written to the game files, the ROM. For Mario Kart 64, the reason it exists is because the ghost data for time trials was written with the intention for the disk drive, and then when they realized the disk drive wasn't going to make it in time for production, they sort of hacked it into the controller pack. They allow you to save 2 ghosts to the entire controller pack. It takes up the entire pack's data, and about 70%, I think, of the data is unused for a typical time trial. They had no way to know how much data the time trial would take up. If it takes frame by frame player input, and it compresses it into an MIO0 block compression. That way the game is able to read it back out using the decompression algorithm and play the ghost. So because of that fortunate inclusion, we can technically load the game in an emulator, write our data into the RAM, run a custom function to compress the data at that section of RAM, and then take the output and write it to a file. That's, of course, absolutely ridiculous. That would be a hilarious way to have to deal with this, and it's entirely unwieldy to think that that would be a reasonable method to compressing the data. Instead, again, Micro has a cheat that's hopefully going to help us here. What he does, and we're going to take a look at that right now. So here I have his segment 6 data from Micro Mountain, and here I have his compressed segment 6 data from Micro Mountain. The MIO0 header is at the start of every MIO0 file. First 4 bytes are a string, MIO0, so that you know for certain and you can verify that this data that you've been pointed to is actually compressed data before you start trying to parse it. The next 4 bytes are an int32 that represents the size of the data that was compressed. If you look here, you'll see that we have 9FD8 bytes for the uncompressed data, which is written here. The next 4 bytes would be an offset to the compressed data. There isn't any. The next 4 bytes would be the offset to the uncompressed data, and you can see here that that offset is hexadecimal 1410. Following that are instruction bits. So you have 8 bits per byte. If a bit is 1, we write 1 byte from the uncompressed data offset, and we advance that by 1. If the bit is a 0, we go to the compressed data section, and there will be basically a list of instructions of what bytes already exist in the stream that we have to write. Again, we're kind of chasing our own tail with that, so it's going to say at byte 5 until byte 25, write this data, blah, blah, blah. For Micro's case, for this compression, we're never going to have a 0 bit because we don't actually compress any of the data. If we go to offset 1410, you will see the entirety of segment 6 has been written out in the uncompressed data section, 9FD8 bytes. And here we have exactly enough bits to represent the instructions needed to write all of those bytes. So if we were to take 9FD8 and divide it by the 8 bits that exist per byte, we end up with 13FB, 5115, 5115 bytes. We have to add 16 bytes because of the length of the header, which would bring us up to 5132. We also need to account for a 32-bit address. All of the addresses here, both for the compressed data and the uncompressed data, as well as the address that the entire file starts at, all need to be at 32-bit addresses so that they line up nice and pretty like you see here in my hex editor. For that case, if we had gone to 5131, we could have gone just 1 byte ahead and we would be at a 32-bit address. Micro perhaps did this by hand or however it was calculated, I'm not sure. Instead went an extra 32 bits ahead. These would never have gotten read. Once the instructions lead the output file to be the size listed here in the header, the algorithm stops. It stops writing, it stops reading, and it says, okay, I have decompressed the file, it is written here, I have done my job, I'm all finished. So what this hack does is it forces the decompression to read from the uncompressed bytes, and 1 byte at a time, it will write out the entirety of the uncompressed data section. As you can see, the file ends up, for segment 6's case, about 5 kilobytes larger. This will be, I imagine, exactly 1/8 plus 16 bytes, because you need 1/8 plus 16 bytes, and then a smidge for the alignment to the 32-bit address. For that reason, it's actually almost uncompression because the data ends up larger than the input file. But again, it will allow the game to read it, to store it into the proper memory address, and this will allow me to know for certain if the issue is with the compression algorithms that I'm using, or if the issue is something else that's clobbering the memory at that address. If you look here, this is what it should look like when segment 5 is packed or extracted and written end to end. And this is what I pulled out of the RAM. And you'll see that right around the area 7,000 bytes in or so, after the end of the or at the end of the fence, it corrupts, and you can see that the fence kind of gets redrawn again and again and again all the way down. What I apologize, I zoned off. What I did to make sure that this wasn't just an issue with the texture, I had actually had this flipped originally, and it was this texture here, this green texture, that was crashing and being written to the end. I drew a new texture, saved it with a different format to make sure that it wasn't an error with the way that the texture was being written by the libraries with texture 64, which I'm using to convert the bitmap data. And then as a final test, I reversed the order of the textures and then still had a crash again, or an error with this texture getting decompressed. I assume, again, that it's some issue with how those bits were being read and written, and that it's just an incompatibility between the two. Again, I'm hoping that with this hack workaround that Micro used, we won't have this issue and we'll be able to get the course loaded and move forward. Again, not a perfect solution considering that the data ends up larger than when we started, but it's not a significant amount of data. As opposed to adding about 120 kilobytes, 130 kilobytes, we added about 380 kilobytes, a little less than 400. So when you're talking about a limitation of 64 megabytes for the entire ROM and starting off at only 12 megabytes, that's a lot of room. So I'm not too concerned about this being the solution. If it is rather sloppy, and it's unfortunate that that's the case. But if it gets the job done, that's what I'm most concerned about. Again, this is what has been holding me back at the moment, is diagnosing this and figuring this out, as well as figuring out all the other things with course paths and some of the other recent work I've had to do. So I appreciate, I've noticed a lot of interest in some of the other videos I've been posting as a sort of holdover, and I do appreciate everyone's interest in Mario Kart 64 modding, and hopefully I'll have a much better update in the next upcoming days. So if you would like to be kept up to date and you have not already subscribed, please feel free to click the subscription link that is down below, or that'll be popping up on the video in just a minute or so. I do cover, on top of custom courses for Mario Kart 64, other modding that goes on both by myself and others in the community. Try to keep up with all the progress and different things that we've been doing. So it is definitely a great channel to keep up on Mario Kart 64 modding if that's something that you're interested in doing. I want to thank everybody for their interest and for watching this video and their interest in this. And again, just thank you guys so very much, and I hope you all enjoy the rest of your day. Take care.